wabarakatuh. We from Group 2, we want to present about the overview of control flow hijacking attack and defense techniques for process. This is our group member, ALIFAFIF, Arfan, Abu Alif, and Hakim. And for the introduction, since Morris used the buffer overflow vulnerability to write a worm to paralyze many network computers in 1988, network attacks, especially control flow hijacking attacks, have brought huge economic losses to the country and society. Control flow hijacking attack is a common attack on computer software, which can change the control flow of the process through vulnerabilities such as buffer overflow to perform malicious operation. For the control flow hijacking attacks, researchers have proposed and implemented several protection techniques, offensive and defensive sides of interdependence, the continuous development of evolution. Basic principles and the latest progress of control flow hijacking attacks and focus on the related defense technologies based on defense ideas and analysis and comparison. Summarize and analyze the related technologies of flow hijacking attacks and defensive, which has certain theoretical value and practical significance for researchers to design more reasonable and practical defense technologies.
Hi, and Assalamualaikum warahmatullahi wabarakatuh. My name is MOHAMMAD. My mention number is B0819100066. So I will present about my part 2.0, 2.1, 2.2, and 2.3. For 2.2 is about recent status of process control flow hijacking attack technology. So the attacker need to know firstly which one is CPU or OS that's running in their target. Then the control for hijacking attack can be done. So right here I have classified two types of attack that easier to understand. Firstly, code injection attack, and the other one is code use attack. So what is code injection attack? The code injection attack is something involving the attacker to inject malicious code into the address space of the attack process by using the input operation of the process, make the process illegally execute. The attacker mostly succeed because of the vulnerable system that not well organized will make the computer to misinterpret data as instruction that need to be executed through it, not receive data. So, the researcher has proposed Data Execution Protection DP, Data Execution Protection Defensive Measure to prevent from any code injection attack. This process will setting the variable part of the process space to be non-executable. So then, we go to 2.2, Code Reuse Class Attack. So what is Code Reuse Class Attack? What we call as CRES is a type of attack that different with code injection attack that is do not require attacker to inject malicious code into the process address space. It's only using the existing instruction in the program or shared library to complete the attack. There are two types of CRE. First, ROP, return-oriented programming, and GOP, jumping-oriented programming. So the most common attack type used that is return-oriented programming. As we know, the root consists of a set of gadget address and data values loaded into memory with the gadget. The gadget is code fragment. The end with the return instruction is using by the attacker by doing the combination into address of each gadget. The attacker will using the stack overflow and other vulnerabilities and it's carefully construct the payload. So, the attacker can hijack the control flow when the execution function return. Then, the malicious can be formed. Next, for GOP. The GOP has one main role that's called dispatcher that will play the critical role in this type of attack. it needs to maintain the virtual program counter. So then we go to 2.3, improvement of code first class attack. Usually, traditional ROP can be defeated by ASLR, and based on the researcher under ARM and SPARC, we know a lot of attackers using code first attack. So how the attacker want to defeat the ASLR? The attacker can using the G-trope technique to defeat the ASLR. What is G-trope? G-trope is just in time. Next, there are another technique that can be used to defeat ASLR to know where the gadget will be in the particular program executable. So there's one technique that's called blind rope or B-rope technique, which introduced at IEEE Security and Privacy Conference in 2014. So how this technique works? The idea is if the server restart or crash but does not compromise, then we can read the stack to leak the canaries. What is canaries? Canaries are secret value placed on the stack which change every time the program is started. So the gadget can be found at runtime to effect call thread. Then the binary can be dumped to find gadget for the shell code using write system call. The blind rope also can be done remotely, so then the system can be exploited. So that is for me. Thank you.
So now we go to defenses against control flow hijacking. To counter control flow hijacking attempts, a number of defense techniques have been developed. Complete memory safety, code pointer integrity, and control flow integrity are some of these defenses. The effectiveness of these countermeasures is determined by how a given implementation balances security and performance overhead. First is complete memory safety. So, by protecting all pointers, complete memory safety can defend against all control hijacking attempts. So, at the first stage, in control hijacking, corrupts a pointer by making it incorrect and then delaying it. When a pointer goes outside the limits of its pointed object or when the object is deallocated, it becomes invalid. A dangling pointer is a pointer that points to an object that has been deleted. A spatial error is caused by dereferencing an out-of-bounds reference, whereas a temporal error is caused by dereferencing a dangling pointer. So this is the figure for the defense mechanism: memory safety, code pointer integrity (CPI), randomization ASLR, control flow integrity (CFI), non-executable data, high-level policies. In the step 6 of the attack step. So, spatial memory safety is provided by memory safety procedures that prevent spatial errors, whereas temporal memory safety is provided by memory safety methods that prevent temporal errors. So, on the CPU benchmark, soft bounding with the CETS additions ensures complete spatial and temporal pointer safety, but at a large cost up to 4 times slowdown, 116% on average. Low overhead mechanisms that trade off security guarantees for performance, such as approximation or partial memory safety procedures, on the other hand, have been found to be circumvented in the past. Fortunately, hardware support can make perfect memory safety practical. For example, internal memory protection at extensions MPX can help enforce memory safety checks more effectively. Secondly, the fat pointer strategy demonstrates that hardware-based approaches can maintain spatial memory safety while incurring minimal expense. Tech architectures and capability-based systems may also point in the right approach for defending against such attacks.
Okay, code pointer integrity or CPI. Unlike complete memory safety, CPI relies on protecting only the integrity of sensitive pointer to thwart control hijacking. Since sensitive pointers make up a subset of all pointers, CPI promises to provide strong security at a very reasonable performance cost. CPI first appropriately identify all sensitive pointers via static analysis of the code. Then it stores metadata for checking validity of code pointer in a designed safe region of memory. The metadata include the value of pointer and its lower and upper bound. Additionally, CPI adds instrumentation that propagate data when pointer operation occur. CPI relies on a secret region which is kept in the same space as the process being protected to be isolated. It assumes it must be leak-proof and cannot be disclosed. However, we show that an attacker can disclose the location of the safe region using the timing side channel attack. Once the location of the code pointer in the safe region is known, the metadata of the pointer is modified to allow the execution of a ROP change. Next is Control Flow Integrity or CFI. CFI thwart control hijacking attack by ensuring that the control flow remains within the control flow graph intended by the programmer. Every instruction that is the target of a legitimate control flow transfer is assigned a unique ID and checked insert before control flow instruction to ensure that only valid targets are allowed. There are two types of control flow transfer, which is direct and indirect. Direct transfer have a fixed target, so one can match against the fixed target address enforcing the control flow transfer. However, indirect transfer, like function call and return, and indirect jump, take a dynamic target address as argument. As the target address could be controlled by an attacker due to vulnerability, CFI check to ensure that its ID match the list of known and allowed target ID of the instruction. Every control flow is permitted as long the CFG allow it. Any CF-based defense relies on the level of coverage of the CFG. If the CFG is perfectly constructed, when we can ensure only the control flow intended by the program. However, perfectly constructing and maintaining CFG ahead of time requires the source code of the program. It's hard and inaccurate and incur very high performance costs. This practical concern demands that we use a weaker version of CFI, which results in a weaker security.
The conclusion: the lack of memory safety in low-level language C or C++ allows attackers to alter the program's conduct or assume full responsibility for it by hijacking its control flow. Our results give extra proof that strategies that exchange of memory security or performance are viable to motivated attackers. Specifically, we present an attack on the recently proposed CPI technique still as an attack that's able to bypass fine-grained enforcement of CPI. For CPI, we show that the employment of information hiding to safeguard the safe region is problematic and should be accustomed to the protection of CPI. We assess the assault utilizing a proof of either exploit on a variant of the engine's web server that's secured with CPI, ASLR, and DEP. We also assess the work factor needed to sidestep different executions of CPI, including various potential threats to the underlying execution of CPI, including variety of possible fixes to the initial implementation. We show that information hiding can be a weak paradigm that always finishes up in vulnerable defense. We show that for styling control jujutsu by utilizing more exact pointer investigation algorithm is difficult for real-world application. Our result also to assault on reasonable protective methods feature the need for complete memory security. Additionally, the fact pointer schemes and tag architecture present a possible direction for mitigating control hijacking attacks just like the attacks presented during this incident. That's all from us.